Mixtures of dispersed combustible materials, such as gaseous or vaporized fuels, and some dusts, and air will burn only if the fuel concentration lies within well-defined lower and upper bounds, determined experimentally, referred to as flammability limits or explosive limits. Combustion can range in violence from deflagration through detonation. Limits vary with temperature and pressure, but are normally expressed in terms of volume percentage at 25 degrees Celsius and atmospheric pressure. These limits are relevant both to producing and optimizing explosion or combustion, as in an engine, or to preventing it, as in uncontrolled explosions of buildups of combustible gas or dust. Attaining the best combustible or explosive mixture of a fuel and air, the stoichiometric proportion, is important in internal combustion engines such as gasoline or diesel engines. The standard reference work is that by Zabetakis, using an apparatus developed by the United States Bureau of Mines. Violence of combustion. Combustion can vary in degree of violence. A deflagration is a propagation of a combustion zone at a velocity less than the speed of sound in the unreacted medium. A detonation is a propagation of a combustion zone at a velocity greater than the speed of sound in the unreacted medium. An explosion is the bursting or rupture of an enclosure or container due to the development of internal pressure from a deflagration or detonation as defined in NFPA 69. Limits. Lower flammability limit. Lower flammability limit. LFL. The lowest concentration, percentage, of a gas or a vapor in air capable of producing a flash of fire in presence of an ignition source. Arc. Flame. Heat. The term is considered by many safety professionals to be the same as the lower explosive level. LEL. At a concentration in air lower than the LFL, gas mixtures are too lean to burn. Methane gas has an LFL of 5.0%. If the atmosphere has less than 5.0% methane, an explosion cannot occur even if a source of ignition is present. Percentage reading on combustible air monitors should not be confused with the LFL concentrations. Explosimeters designed and calibrated to a specific gas may show the relative concentration of the atmosphere to the LFL, the LFL being 100%. A 5% displayed LFL reading for methane, for example, would be equivalent to 5% multiplied by 5.0%, or approximately 0.25% methane by volume at 20 degrees Celsius. Control of the explosion hazard is usually achieved by sufficient natural or mechanical ventilation to limit the concentration of flammable gases or vapors to a maximum level of 25% of the lower explosive or flammable limit. Upper flammability limit. Upper flammability limit. UFL. Highest concentration, percentage, of a gas or a vapor in air capable of producing a flash of fire in presence of an ignition source. Arc. Flame. Heat. Concentrations higher than UFL or UEL are too rich to burn. Operating above the UFL is usually avoided for safety because air leaking in can bring the mixture into combustibility range. Influence of temperature, pressure and composition. Flammability limits of mixtures of several combustible gases can be calculated using Le Chatelier's mixing rule for combustible volume fractions. X I display style X underscore I L F L mix equals 1 I X I L F L I display style LFL underscore text mix equals frac 1 sum underscore I frac X underscore I LFL underscore I, and similar for UFL. Temperature, pressure, and the concentration of the oxidizer also influences flammability limits. higher temperature or pressure, as well as higher concentration of the oxidizer, primarily oxygen in air, results in lower LFL and higher UFL. Hence the gas mixture will be easier to explode. The effective pressure is very small at pressures below 10 millibar and difficult to predict, since it has only been studied in internal combustion engines with a turbocharger. Usually atmospheric air supplies the oxygen for combustion, and limits assume the normal concentration of oxygen in air. Oxygen-enriched atmospheres enhance combustion, lowering the LFL and increasing the UFL, and vice versa. An atmosphere devoid of an oxidizer is neither flammable nor explosive for any fuel concentration, significantly increasing the fraction of inert gases in an air mixture, at the expense of oxygen, increases the LFL and decreases the UFL. Controlling explosive atmospheres, gas and vapor. Controlling gas and vapor concentrations outside the flammable limits is a major consideration in occupational safety and health. Methods used to control the concentration of a potentially explosive gas or vapor include use of sweep gas, an unreactive gas such as nitrogen or argon to dilute the explosive gas before coming in contact with air. Use of scrubbers or adsorption resins to remove explosive gases before release are also common. Gases can also be maintained safely at concentrations above the UEL, although a breach in the storage container can lead to explosive conditions or intense fires. Dusts also have upper and lower explosion limits, though the upper limits are hard to measure and of little practical importance. Lower flammability limits for many organic materials are in the range of 10 to 50 grams per cubic meter, which is much higher than the limits set for health reasons, as is the case for the LEL of many gases and vapors. Dust clouds of this concentration are hard to see through for more than a short distance, and normally only exist inside process equipment. Flammability limits also depend on the particle size of the dust involved, and are not intrinsic properties of the material. In addition, a concentration above the LEL can be created suddenly from settled dust accumulations. So management by routine monitoring, as is done with gases and vapors, is of no value. The preferred method of managing combustible dust is by preventing accumulations of settled dust through process enclosure, ventilation, and surface cleaning. However, lower flammability limits may be relevant to plant design. Volatile liquids. Situations caused by evaporation of flammable liquids into the air-filled void volume of a container may be limited by flexible container volume or by using an immiscible fluid to fill the void volume. Hydraulic tankers use displacement of water when filling a tank with petroleum or SUR. Examples. The flammable, explosive limits of some gases and vapors are given below. Concentrations are given in % by volume of air. Class IA liquids with a flash point less than 73 degrees Fahrenheit, 23 degrees Celsius, and boiling point less than 100 degrees Fahrenheit, 38 degrees Celsius, have a NFPA 704 flammability rating of 4. Class IB liquids with a flash point less than 73 degrees Fahrenheit, 23 degrees Celsius, and a boiling point equal to or greater than 100 degrees Fahrenheit, 38 degrees Celsius, and Class IC liquids with a flash point equal to or greater than 73 degrees Fahrenheit, 23 degrees Celsius, but less than 100 degrees Fahrenheit, 38 degrees Celsius, have a NFPA 704 flammability rating of 3. Class II liquids with a flash point equal to or greater than 100 degrees Fahrenheit, 38 degrees Celsius, but less than 140 degrees Fahrenheit, 60 degrees Celsius, and class IIIA liquids with a flash point equal to or greater than 140 degrees Fahrenheit, 60 degrees Celsius, but less than 200 degrees Fahrenheit, 93 degrees Celsius, have a NFPA 704 flammability rating of 2. Class IIIB liquids with a flash point equal to or greater than 200 degrees Fahrenheit, 93 degrees Celsius, have a NFPA 704 flammability rating of 1. See also, flammability, limiting oxygen concentration, minimum ignition energy. Further reading. David R. Lyde, Editor-in-Chief, CRC Handbook of Chemistry and Physics, 72nd edition, CRC Press, Boca Raton, Florida, 1991, ISBN 0-8493-05659-9.